Complex zeros of polynomials. Think about what a complex zero is. Example. For example, like x equals 2 plus 3i is a complex zero, right? So it's a real number plus an imaginary number. That would be a complex zero, which it is possible to have complex zeros of polynomials. So let's focus on a few things here. Complex zeros of polynomials occur in conjugate pairs. This is really important. Okay, it says let f of x be a polynomial function that has real coefficients. If a plus bi, where b does not equal 0, is a 0, then the conjugate a minus bi is also a 0 of the function. A plus bi and a minus bi. They come in pairs. That's really important. So if you're ever given a problem, it tells you that 2 minus 4i is a 0. You also know that 2 plus 4i is a 0. Factors of a polynomial. Every polynomial of degree n is greater than 0, real coefficients, can be written as a product of linear and quadratic factors with real coefficients, where the quadratic factors have no real zero. Okay, so ultimately this is just saying that we can always write a polynomial as a product of linear factors, but also we can write it as a product of quadratic factors if the quadratic factors have no real zero. So let's look at this example. Find a polynomial with real coefficients with the following zeros, given 0, -1, and -2i. So let's just take a minute here to think about what our zeros really are. Our zeros are x equals 0, x equals -1, x equals -2i. And because that's an imaginary number, or really a complex number, complex 0, we know that positive 2i, must also be a 0. If I'm to write 0, x equals 0 as a factor, that's just x, or x minus 0. X plus 1 would be, x minus, oh my goodness. X equals -1 as a factor would be x plus 1. You knew what I meant, right? And we have x plus 2i and x minus 2i. Does it matter the order in which any of these are written? No, that's because of the commutative property of multiplication, right? So this is written as a product of linear factors. If we wanted to go even a step further, here, you gotta get that color back. It's important. I have x squared plus x. And then if I multiply these two together, I would get x squared plus 4. Don't believe me? Multiply them out. Okay? Which finally, if I multiply these guys together, I should get x to the 4th plus x cubed plus 4x squared plus 4x. Okay? Again, if you're wondering where some of these came from, then just go the longhand way and multiply it term by term. But you should get this as a polynomial with real coefficients. All these are real. And it has these zeros. Next example. It says, find all zeros of f of x, given that 1 plus 3i is a 0. So if 1 plus 3i is a 0, we also know that its conjugate pair, which is 1 minus 3i, is also a 0. Also, by the way, make sure you save some room for yourself in your notes packet. This is going to require a bit of work here. So if I write those zeros as factors, that's going to be x minus this number and x minus the other number. Cool. So now I'm just trying to simplify this a little bit so that way I can use their product to do long division with this polynomial. Now I can use that associative property from back in the day, and now I can have x minus 1 plus 3i, x minus 1 minus 3i. Why did I do that? Well, because now this looks like a difference of squares, almost. Okay, so now I have x minus 1 squared minus quantity 3i squared, which this x minus 1 squared is x squared minus 2x plus 1. And if I think about what 3i squared is, that's 9 times negative 1, but I have a negative in front, so that's a plus 9. So last but not least, let's just simplify this here. I have x squared minus 2x plus 10. So again, the purpose of me doing this is because I have these two zeros, and I wrote those as factors. So this quadratic right here has the two factors of these complex zeros. Now that I have that, so this is like a little side work we had to do before the problem. Now that I have that, I can use long division. Everyone's favorite. Don't forget, if I was missing a term in here, I want to have placeholders. So I'm dividing x to the fourth by x squared, which should give me a solution that is x squared, which would give me my other two zeros. That's what we're all right, here we go. Let's have you guys right now go ahead and pause me and do the long division part on your own. All right, go ahead. Okay, so hopefully you went through long division and got a zero remainder, which makes sense because I just divided by 2 of my zeros, right? So I should get a zero remainder. Now I have this x squared minus x minus 6. If I set that equal to 0, I should be able to find out my remaining two zeros. So let's answer this guy. All right, so right here, I can see what my 4 zeros are. Okay. Yeah, for the zeros, not the x. So I have my zeros are x equals 1 plus 3i, 1 minus 3i, 3, and negative 2. Last example. We are going to write this function as a product of factors that are irreducible over the rationals, or that of factors that are irreducible over the reals, and the product of linear. So let's start by just going through it. Boom, boom. Now, x squared, multiply 3 and 36 9. Should get plus 12 and minus 3. So here we have two factors. Both of them are quadratic, however. So let's keep breaking this down. So let's do x squared plus 12, because if I break this one down, I'm going to get some imaginary numbers in there. This part here would be x plus root 3, x minus root 3. These were irreducible over the rationals. These were irreducible over the reals. Last but not least, let's get a product of our linear factors. that'll be by breaking down this guy. Which, if you're not sure, is it x squared plus 12 equal to 0? Equals plus or minus the square root of negative 12, which is equal to plus or minus 2i root 3. So here we go. X minus 2i root 3, x plus 2i root 3, and the other two that I had from before. Look how smart we are. All right.